Thank you. Right. Thanks, Allison. And I want to thank a few other people. In particular, Ruchika was the one who extended the invitation. Oya was the one who's been coordinating a lot of this. Other people, Paul's helping out with technical side of things. William escorted me over here this morning. So a lot of people involved, and thank you all for being here as well. Before we start, I just wanted to do a few logistics things. We do have a lot of people here. I'm astonished that so many people showed up, but this is great. There is a schedule on a link that I sent out. And in case you didn't get that, if you go to andysbrainblog.com and then you click on workshops and scroll down to the one that has Ohio State University, this has our agenda for the next 2 days. And ahead of time, let me know if anybody didn't get any instructions, and we can talk during one of the breaks. But I'm assuming everybody has MATLAB installed and didn't have any problems. They also were able to download and install the contour box. I didn't hear anything, so I'm assuming that all that went totally fine. I mean, things do come up. Just be aware that we don't have that much time to troubleshoot installation issues. But say during the lunch break or maybe during one of the smaller breaks, if there's a small question, I can address it. Now, you'll see a couple things here. Today we're starting at 9:30. Tomorrow we're starting at 9 a.m. Same place. I apologize for making it a little bit earlier, but that's just the way that the whole scheduling worked out. And at the end of today, I'll be meeting with Kelly and Jean-Marie, yeah. And then tomorrow it's going to be with Anita and Mike, I believe. Okay. All right. Just making sure we have all that squared away. All right, so keep this tab open because it has links to a few things that I'm going to be referencing to later. There'll be scripts, there'll be small data sets that I'm going to ask you to download to follow along with practicals. The format of this, I'll be lecturing a little bit, then we'll have some hands-on exercises. I'll talk some more, we might have a break, and we'll just kind of see how that flow works, but I think it should work out pretty well. The other thing, and this is something that Allison alluded to, is a relatively new project I've been working on for the past year or so called Andy's Brain Book. So I've had the blog for a while. That was just kind of a side project for a long time, and this is my attempt to make it more systematic, more coherent. What I'm hoping is that we don't have a lot of time, both today and tomorrow, to go through a lot of topics. So you requested fMRI pitfalls and also functional connectivity, the contour box. It's a lot of stuff. And what I'm hoping to do is give you enough of a foundation where you're able to then use that to analyze your own data and also data sets that I point to. Right? So there's these open access data sets, there's Open Neuro, there's the Human Connectome Project data as well. So in case you can't find it, if you just Google Andy's Brain Book, it should be the first that comes up. The address is right here, andysbrainbook.readthedocs.io. Should be enough to get you there. Keep that open as well because that also has a few animations, some other links that I think will also be useful. And while I'm here, I'm just going to give you a brief tour to get you oriented. This is still a work in progress, but it has modules on things like if you've never used Unix before, right? There's a short walkthrough with that. And just to give you a sense of how this works, it's organized with things like overview, what you're going to cover, demo code that you can use on your computer, and then at the very end, might have exercises and also a video, which we're not going to watch this whole thing, obviously, but for example, there will be tables of contents indicating what we'll be talking about. So for example, if you want to see an animation about how a for loop works, you can skip to that and get to what you need quickly. Somebody gives a thumbs down. That's not good. Who did that? Okay, but just keep this open. I will be coming back to it. I'm also assuming that there's a range of experience backgrounds here, right? Some people may have never even opened MATLAB, and that's fine. We should be able to stay on the same page. I'm also hoping to give material for more advanced users. Maybe you've actually done functional connectivity analysis before, but you haven't used the contour box. And you want to know more about what are the most up-to-date methods for doing motion scrubbing, motion correction, ICA, and all of that. So just be aware, we're trying to interweave a few different things here. If you feel like it's a a little slow. That's partly by design, but we're going to try to make it something for everybody. Okay. Any questions about that? Any trouble loading those pages? Okay, so that should be all squared away. Now let's begin with our first lecture, which is going to be on fMRI pitfalls. I had this slide, but Allison's already talked about it. I've lived in Columbus, I've lived in Indiana, I've lived in Michigan, Ann Arbor. So something for everybody to hate, right? So I hope people won't hold that against me, but I've really liked all three of these cities, so I have nothing against it. And just one more thing, just one more kind of brief background thing about me. I'm part of something at the University of Michigan called the Neuroimaging Initiative, which may be of interest to some of you. I believe Ruchika Prakash is trying to build something similar here as well. It's a collaboration between any kind of imaging researchers at Michigan. So if you use the MRI scanner and you collect either fMRI data, structural data, diffusion data, you are entitled to my time as a consultant. So if you have questions about how to set up an analysis or analyze data that's already been collected, you can talk to me. I mean, that's really my job. I have an office in the psychology building. And this covers things like fMRI analysis, structural analysis with FreeSurfer, and diffusion analysis, to name a few. For longer term, we're trying to branch out into other modalities like EEG, for example, maybe TMS at some point. But for now, it's primarily anything that's gathered off the scanner. If you want to talk more about it during some of the breaks, I'm happy to do so. Okay. So today, as I mentioned, is going to be mainly pitfalls of fMRI analysis. And then we're going to start talking about what are some of the main problems both with task-based and resting state analyses that, you know, a newcomer to intermediate level user should be aware of. And we'll finish today by talking about functional connectivity, and in particular the Kahn toolbox. I like this toolbox a lot because, one, it's kept up to date. The primary developer, his name is Alfonso Nieto Castañón. He was working with the Whitfield Gabrielli lab at MIT, I believe. I don't know where he is right now. I think he still has an affiliation there. But he keeps it up to date, a couple new releases every year, I think. The most recent version is 19B, so he's been working on this quite a bit. And he really stays up to date with what the most current practices are for cleaning the data and analyzing the data. It seems to just be very, I don't worry as much about whether he's staying on top of what the recommended practices are. And it's a very easy toolbox to use for both beginners and more advanced users, which is why I like it. But to start, we will begin with pitfalls of fMRI analysis. So I'm going to start talking about something called the multiple comparisons problem, because that has really percolated into a lot of different kinds of errors that people can make when analyzing fMRI data. This was a review published a while back by Alvin Feinstein, and this was really focusing on methods of epidemiological studies. So we've all come across this. It's almost become a punching bag of sorts, in which researchers will establish some kind of correlation or association or link between bananas and cancer. You eat too many of those, you're gonna. I mean, there's some kind of association. You know, we analyze 5,000 people and their genome, and you know, at some point, if you analyze enough people and you look at enough variables, obviously you're going to find some kind of significant association between them. Most everybody here is aware of that. It's a pretty basic idea in stats class. But there are also more insidious things also tied up with that, such as hypothesizing after the fact. So you only select certain analyses that after you've analyzed everything are significant, and then only report those. And then the more basic error of just failing to correct for multiple comparisons. So you do enough tests, by chance you're going to get a certain false positive rate. And if you don't correct for that, you're going to find false positives. So that's nothing new. It's been known for a while. But we apply this to imaging data, and we collect these images that are like these gigantic Rubik's cubes, right? It's like a giant cube surrounding the brain, and it's made of individual cubes, which we call voxels. That's how we split up these three-dimensional images that we collect from the scanner. And in a typical scan, depending on the resolution, if it's really high resolution, you can get as high as 400, 500,000 voxels at these very high resolution scans. So even when you do a pre-processing step called smoothing, which I'll talk about later, tens of thousands of independent tests still remain. So a voxel and its neighbor are going to share a lot of information. It's not a true independent test between the two of them. Okay, we'll talk a little bit more about the details later. But the whole point here is you do have many, many thousands, tens of thousands of independent tests that you're doing, and you got to correct for all of them in a typical fMRI data set. Now, again, that seems pretty obvious, but back in about the late 2000s, some researchers were finding out that a lot of these statistical analyses a lot of researchers were carrying out had some flaws in it. And to just drive this point home about the multiple comparisons problem, I was working here actually when it came out, when a lot of these papers I'm going to talk about came out. This is the so-called dead salmon study. I'm sure a lot of people have seen this. I don't know if it was published as a paper, but it was definitely a poster, and it made the rounds. A man named Bennett, I forget his first name, but anyway, he just put a dead salmon inside the scanner. Which, you can put anything inside the scanner. You can put fruit in there. You can put objects and kind of see the insides. It's pretty cool. But he said, well, what if I put something in there which I know to be inanimate, dead, there's no neural activity at all, and I run the basic pre-processing and analysis stream I would on a typical human subject. Well, lo and behold, they showed this salmon things like emotional pictures, people with scared faces, angry faces, and compare that to a control condition, just the way I would with scanning any person here. And you will see that, you can't see my mouse, but whatever, you can see it right here. There are actual voxels lighting up in the brain right about here. You don't have a big brain, but you do have voxels to parcellate it. And if you don't correct for multiple comparisons, this is something that you would find. So obviously, the punchline was, well, does the dead salmon have a neural response to pictures? Yes or no? Well, obviously not. But this goes home to show that you do need to correct for multiple comparisons to not get this kind of false positive. Because a lot of people simply weren't correcting for multiple comparisons, and it was causing a big, big problem. Okay, so those are all pretty easy examples to understand, and I'm sure most people have had enough of it drilled into them that they should be correcting for multiple comparisons. But let's move on to some more insidious examples, and these still come up. I was asked by a reviewer to do one of these analyses, so it's still out there. You got to be aware of when this happens. And I'm going to start with an example of a beverage product called Loko. Okay, there's some laughs, so some people know what this is. According to my research, I was alive when this. Well, I was here. I was here when this thing first hit the shelves, and as far as I can tell, this was designed to seriously injure, maybe even kill young people, specifically young men, because this thing contains I think, correct me if I'm wrong, some people probably know this, it's something like 6 shots of alcohol and 4 cups of coffee. It's something crazy. I mean, this is something absolutely ridiculous. They may have banned it here in Ohio. Did they? Okay, good. I saw somebody pour it out once, and it's like this substance. It's like the color of troll doll hair. You know what I'm saying? It's really weird. Anyway, let's say, for example, that I conduct a study in which I want to determine whether the consumption of Loko before some math test improves scores or has no effect or decreases scores. I don't know, something like that. And I test this on, this is my idea of what, say, freshmen look like. I don't know. They seem to just get younger all the time. It's very strange. They seemed like adults when I was a freshman, but now they seem a little young. But let's say that I give a random sample of them this Loko drink, and I have them take a test. And I find out that, only half of them score higher after drinking 4 Loko. So I'm only going to focus on those people. And I find that after I run my statistics, that there is a significant effect. And I report this bar chart, and I have the error bar, and it's all done just like you would with a basic inferential stats test. Okay, so I've gone through the trouble of giving you a very ridiculous example to really drive this point home that this is, in fact, a bias analysis, also called a circular analysis or non-independent analysis. These really all refer to the same thing. Circular is, in my opinion, it's probably the most informative label to use in that I run an initial test. I find that there's only a certain subset of people who have scored in the direction that I want. Then I only take those people and run another test on them. So it's circular because I go, well, it's significant because their scores were significant, and that's kind of a circular idea. Another kind of funny story about this, I was trying to explain this. This was a while ago when I first read this paper to a friend of mine because he was trying to do a circular analysis, and he wasn't aware that that was a problem. And I said, well, that's biased. And he said, well, why is that? And I said, well, because it's circular. And the irony was lost on me. But anyway, so to be a little more explicit about that, you're simply taking results that are always significant and then testing again for significance. And then if you're surprised that it's significant, that really shouldn't be a surprise. That's just by definition, you've biased it towards being significant. Another term is called double dipping. So whichever of these labels helps you remember this type of statistical fallacy, just run with that. Nicholas Kriegis-Korta wrote a really good paper back in 2009, and I think double dipping is in the title. It's a very good paper. Okay. I'm going to break out of this quickly because I have some images up on my book. You may see me doing this once in a while. Just I hope this isn't too much of a break in continuity. But let me see here. If you want to follow along, it's under fMRI appendices, bias analysis. If you have trouble finding it, if you just say, enter in this search field something like bias analysis, it should be the first result that comes up. So another useful feature about the book. If there's a topic I'm talking about, like I talk about smoothing, but I don't really, you don't feel like I explain it that well, I do have more text and illustrations if you want to go back and look at some of that. Anyway. Okay. So let me blow this up a little bit. Back in 2006, so there were some papers that came out highlighting the same circular analysis problem that I'm talking about right now. But it really came to a head in 2009, which I'll get to in a second. Back in 2006, let's back up a little bit more. From the lab of Grillspector et al., they did an analysis of the so-called fusiform face area, right? And they want to know, is it selective for certain categories? Is it selective for faces as opposed to, say, animals, cars, sculptures, inanimate objects? And they did the same kind of bias analysis I'm talking about right now. In other words, they ran an initial test, and let's say these red voxels right here, those were the significant voxels for the contrast of, say, face stimuli versus all the other stimuli. And then they go into those same voxels, the voxels that are already significant, and they do another test. And lo and behold, those are significant. And they do that for all the different categories. So they find this really beautiful interaction across all these different categories. I should say they find a strong effect for each of them in these separate regions that they determined by doing an initial test. Okay. But a year later, Baker and colleagues come back, they write a letter, and they say, well, if we do the same thing, but they do it with a non-brain ROI. So imagine that they do this same analysis, but they find voxels that are outside of the brain. If you've ever done an fMRI analysis, you will find significant voxels, if you haven't corrected for multiple comparisons, outside of the brain. And they do the same thing. They look within those voxels that are outside of the brain, and they get this exact same pattern. Think back to the salmon article. Obviously, if there's a voxel outside the brain, there's no actual neural activity there, so what gives? And if they did the exact same thing with the original data, but they used so-called unbiased analyses, which I'll get to in a second, they find that overall, in this unbiased ROI they use, there's a strong effect of the face stimuli, but there's no evidence that there are selective areas for, say, animal, car, and sculpture. All right? This is the first known instance that I know of in which circular analysis had been a really big, say, methodological issue addressed in the literature. So if I go back to this presentation, and this all came out during, again, my time here, so I have pretty vivid memories about this whole thing. Back in 2009, in the good old days, there was a paper published by a man named Ed Vool and a few of his colleagues, Pasher and Winkelmann, I think, if I'm getting those names right. And they saw things like the Grill Spectre paper. They saw other analyses being presented, and they thought, you know, this is a little weird. We're finding these really, really high correlation values, especially in, say, social neuroscience. I don't mean to, you know, kick someone while they're down, but social neuroscience has really gotten the brunt of this whole reproducibility crisis thing in neuroimaging, for better or for worse. I'm just telling it like it is. And they also picked up on this back in 2009, because in social neuroscience, a big analysis that people like to do is individual differences. So if you collect something like I always come up with bad ones, but age is the really vanilla kind of uninteresting one. I don't know. Anybody here in social neuroscience, what do you, individual differences, what are some, yeah?
Yeah, we look at pediatric population.
Okay.
Who's sustained a brain injury and kids who have it.
Okay, okay. And are there any like continuous variables you also look at?
Things like incidence severity,
Okay. Mm-hmm.
We also look at assessment measures of IQ.
Okay. So, okay, great. So maybe something like injury severity or something. You do an fMRI task, some basic task like faces versus houses, I don't know, whatever. And then within a region of interest, within a say, circumscribed set of voxels that you're doing an analysis for, you extract that, you correlate it with this individual difference measure, and you see what the correlation is. And they were finding these really, really high correlations being reported a lot of the time. And this was a histogram of what they found when they sent out a survey to several dozen different imagers. I think they were primarily social neuroscience, if I have that right. But they found that mathematically, they determined like an upper limit on what they really should be finding. So if you have like a really, really strong effect for these sample sizes they were dealing with, the maximum estimate for this R value should be something like 0.74. And obviously, a lot of people were reporting values above that. And if I color code this so that I highlight in red which of these studies are bias analyses or non-independent, which are independent, and which ones were not reported, you see a distribution like this. So obviously, the ones that are reporting the highest are disproportionately represented by the biased analyses. Okay, so Vool's interpretation was that this was leading to inflated effect sizes. Okay, notice this isn't a problem with multiple comparisons. That's a slightly different issue, but this is how you select which voxels to test for significance. And his theory was, well, significant voxels are more likely to get a boost from surrounding noise. And this leads to inflated effect sizes. Hard to describe in words, so let me show you an animation of how that whole thing works. I I have a little script that I'm going to read, so this might sound a little wooden, but I think it'll work. So we'll see. Okay, so let's investigate this some more. Here's a z-statistic map showing, let's say, like a group level effect. You can kind of see the outline of the brain there. If we zoom in, you can see the boundaries of each individual voxel. And let's say the range of z-statistics in this image is about 0 to 3. Okay, so brighter ones are more significant, darker, less significant. And assume that there's a real effect outlined in orange. If we extract the parameter estimates for each subject just from those voxels, let's say the true effect is 0.3. Okay, that's my true effect size, something like that. Now, if we threshold our image at an uncorrected level of, say, 0.05, which is a z-statistic of 1.65, the voxels highlighted in red are the only ones that are going to pass that threshold. So notice that some of the voxels overlap with the true effect, but there are also some kind of random ones that are due to noise, but it's only going to capture those that pass the threshold. It's not going to capture any ones that are lower than the threshold, so it's being biased towards a more inflated effect size, which is plotted right there. Let's say 0.7. Now lastly, if we use an independent ROI, I'll give you some examples of how to do that. We'd create a region that, say, encompasses some true effect voxels, some noise voxels, but the key point here is it's not going to be biased towards either the really high significant voxels or the low voxels. It's going to be impartial as to which is which. And let's say that the unbiased effect is 0.2. It might be 0.4, it could be something like that. The key point is it's not going to be biased towards either being low or high. So let me freeze frame that. Any questions? Because this is kind of it can be a difficult concept to grasp the very first time around. Yeah?
Yes. Wait, how are you getting the voxels? Is that just like doing an analysis to look straight at like what the significance is in like a whole brain analysis?
Yeah.
Where the red is coming from?
Yes, yeah, that's where the red is coming from. So in red, that's only going to show you voxels above, say, a certain brightness threshold. That's how I got those. And the point was that, so the true effect voxels, I don't actually know where they are, but if I ran a simulation, I would know. And they've shown this in other papers. But the point is, if I then look within the voxels in red, yes, some of them are the true effect ones, but it's going to also incorporate some noise voxels, right? But the only ones that it's going to include are the ones above the threshold, which is why it's going to be inflating it. Yeah. Okay. I'm spending the most time on this because it's still an issue. Is everybody familiar with this when I'm talking about like circular analysis, voodoo correlations? Just raise up. I'm curious who's already heard about this. Okay. Okay, so most people, but there are a few who haven't, so it's worth recapitulating. So some of the objections, well, what if I just want to see what's going on? Okay, these are valid questions, and there's no real consensus on it. There is a review paper by Vool, Kriegescourt, a couple other people about what to do with these bias analyses if you do them. And this was a legitimate response by some of the people who were being, say, attacked by Vool, especially Matt Lieberman. He published a rebuttal, which was, well, what if you just want to see what's going on? It's an exploratory analysis. You want to have some idea where the effect is trending. Okay, that's valid enough. But my recommendation, which is basically the same as this review paper I mentioned, is, yeah, it's fine to look, but I wouldn't publish it. Even if you have a bunch of caveats about how it was done, even if you don't include error bars, most people, just their first pass as they're skimming, they're going to assume it's an inferential analysis. They're going to assume that's what the actual effect size was. And that can introduce a lot of problems. So maybe supplementary or something, I don't know. I prefer just to not do it if I can help it. Another thing is, well, doesn't the correlation or the effect, what have you, of the bias analysis, doesn't it actually exist? Oh, okay, yeah, true. You got me there. Assuming you corrected for multiple comparisons, yeah, you can make the claim that it is a true effect, given a nominal false positive rate. But magnitude is also important. That's usually the main, that's what the main claims of the paper usually rest on. If you find something significant, but the effect size is so trivial, it doesn't matter, nobody really cares. Bananas and cancer, I mean, there's probably like, I don't know, maybe there's some kind of link, but if it's so infinitesimally small, it doesn't have any practical significance. And it can also be strongly misleading with these biased analyses. So you may have picked up on the fact that I'm touching upon this whole reproducibility problem, right? This is one of the repeat offenders, I would say, in all of these statistical analyses, are these inflated effect sizes or just failing to correct for multiple comparisons. But another one is with sample size. And there are no real, well, I'm going to give you some answers, but they're not going to be, you're not going to like them. Just be prepared for that. There's other problems with sample size, and these are all tied up. So I'm talking about inflated effect sizes and also small sample sizes. They are all linked together. Because if I have a very low sample size, if I have 9 subjects, which was not uncommon for a lot of these early social neuroscience papers that Vull was attacking, if I find a significant effect, it's going to be what? Small? It can't be. Just by mathematical necessity, it has to be really, really big for it to pass this significance threshold, right? If you only have a few people in your sample, that threshold is going to be very, very high. So if you find something significant, that's the only thing you're going to report. So your power to detect an effect with very small sample size is very low, but the effect size that you will find, if you do find one, is going to be gigantic. And they call this the so-called winner's curse. To show you a couple of graphs of why that might be a problem. People run a bunch of simulations. This has been reported ad nauseum throughout the literature. But yeah, if I have, say, statistical power of 20 to 40%, which you'll probably have with a sample size of 20, 25, 30 or so. Depends on the effect, obviously, but for most studies, within about that range. The bias that you're going to find, this very inflated effect size, tends to go up at an exponential rate. Another viewpoint on this, just another different perspective. So let's say if I have, in this solid line right here, or let's say this dashed line, n of 20, my power to detect an effect size of, say, 0.6 is relatively low, and it's going to trail off quite a bit as the number of subjects also goes down. That curve gets shifted more and more to the right. Basically, all I'm trying to show here is if you have small sample sizes, your effect size you're going to detect is going to be very, very large and probably spurious. The problem is people will only report significant effects. So you run a few studies, you only get one that has a whopping effect size, you only report that, and that's the one that goes into the literature, into the publications. So what to do? Again, I feel like kind of a jerk standing up here and wagging my finger. You should increase n, increase your sample size. Okay, you might go, okay, yeah. Everybody knows that, but I don't have a lot of money. It's a problem, right? I get that. In that case, I don't want to predict the future too much, but with the advent of a lot of these open access websites, these large consortiums of open access data, and we'll see a few examples, it may become a little bit easier to, say, adapt something that's already been run, maybe run a different analysis on it, or use that data that's already been out there to generate a more accurate power analysis before you do anything, right? And there are tools out there. One is called, we don't have time to cover all these, obviously, but one, Neuro Power Tools. if you've heard of it. I do have a tutorial on it. Really cool website, completely web-based, and what you can do is it links up with this other repository for data called NeuroVault. And so if you have some kind of effect you're interested in, like, again, I'm terrible with coming up with examples, but you, sir, what are you interested in studying? Yeah. Pain and Alzheimer's disease? Okay, so you could go onto this website. You could search. You could enter search terms like pain, Alzheimer's, whatever, and it would you would already have access to these maps that have already been run, right? And so they get imported into this other website, Neural Power Tools. You generate a power curve giving you an estimate about how many subjects you would need for a certain power effect. I don't have slides on that, but if anybody's curious, I can talk about that, point to it for one of the breaks, or send it out in an email afterwards. But very useful, very sobering, I will also say, because most of us are used to maybe I'm showing my age here, but most of us are used to running studies of, say, 20 to 30 people. Is that still kind of common? That's what I did back in the day. I don't run too many studies anymore, but some people are going way the other way and running, these huge multi-center studies with thousands of people. That's kind of the other end of the spectrum. But for most people, it's relatively small. And I will say that these power analyses usually indicate for a normal effect size of, I don't know, 0.3, 0.4 maybe, I don't know, something like that. You'll need something like 60, 70 subjects, in my experience. That's a lot, yeah. I'm seeing some raised eyebrows, like you can't possibly be serious, but that's just the way it shakes out. Sorry to say. Another way to address this, possibly, is through pre-registered reports. I don't have much experience with this, and I'm curious if there's anybody here who has done a pre-registered report. They're relatively new. Okay. Oh, you have? Okay. Was it a good experience? Was it easy to do? No, it wasn't? Okay, don't do it then. What? Okay. Yeah. It's a good idea because you register your hypotheses already, and then those get reviewed before you actually carry out the study and the analyses. So they can accept the paper based on the strength of your hypotheses, experimental design, and then regardless of whether you find a null effect, it will still get published. Whether it gets cited is another matter, but I'm not trying to make everybody too discouraged. All right, so to wrap up this section on some of these statistical fallacies and problems that we have, I want you to think about a few different scenarios, and we'll say, is this a problem? Is this something that we should be aware of? Let me give you an example of something I encountered a few years ago from a paper that we submitted at one point. This was an individual differences study. It was with different reading measures like decoding, print exposure, so on, and cortical thickness measurements. And so we found something like this. I mean, it was a whole brain analysis. It was corrected, but we didn't do any kind of ROI stuff. And the reviewer said, well, within the decoding cluster, within the print exposure cluster, what do these things look like? And I thought, well, okay, let's take a look. So within this, thing right here, left anterior SMG, we found a really nice correlation of 0.56, and within this print exposure cluster up here, a really nice negative correlation of negative 0.74. Yeah, you can barely see it, but yeah, it's there. A really nice interaction, right? As you move more anterior, like this region by effect, let's say. Is this a bias analysis? It's a softball. Yeah, it's too good to be true. I mean, this was clearly, those were very, very healthy correlation coefficients. Obviously, they're very significant. And we did the analysis. We didn't publish it, but we simply just reported it back to the reviewer and said, okay, here's what you asked for, but it's probably biased because X, Y, Z. Okay, so pretty simple. What about this? This is some random paper I found. And let's say that they have these three regions here. They're looking at things like prediction error, a conflict effect, and a pain effect. Pain is in magenta, prediction error in green, conflict in blue. And they say something like this in their methods. And they say, okay, there's a second level analysis run for each contrast. For each one, you leave out a subject. And then you extract that subject's contrast estimates from the resulting ROI. Let me put this another way. Let's say we had 20 subjects. I leave one subject out. I sequester that subject. I run the analysis on the other 19. And let's say I find a cluster in this area right here. And then from that cluster, I extract contrast estimates from the subject that was left out. Is that biased or not? Why? I'm kind of jumping to a more advanced idea here, but just from what I said, is that, would you say that's independent, non-independent, and why? It's a little bit more difficult to talk about. Yeah?
You wouldn't have ran hypothesis tests on that subject there, right?
Right.
So I would say it's not.
Okay. Yeah, it's not biased or not?
That is not biased.
Yeah, okay. Anybody disagree? Okay. Yeah, this is something called a, something called a leave one out analysis, in which, you know, if the subject, okay, I realize that if you've never done an ROI analysis, this might be some weird terminology, but just bear with me. If I run an ROI analysis and that subject who I'm running the ROI analysis for, I'm extracting those contrast estimates for, if their data didn't go into determining what that cluster is, it is an independent analysis. That's actually okay. It's a type of cross-validation technique, if you're familiar with that. Again, I'll give you some resources about some ways to do this. We can't cover all of them, obviously, and they get a little complicated, but I will give those later. Yeah?
This might be a naive question. What if you have a whole range analysis and you're looking for a group by age interaction? A group can be whatever the cut of the age is.
Mm-hmm.
If you have a significant F effect, for example, in your multivariate model,
Yeah.
kind of have to extract the value to see the direction it's going in,
Mm.
right? So how would you deal with something like that? Because it could be they cross this way, they cross this way. You don't really know from the brain map, right?
Right.
Then you have to extract the values of them.
In that case, I would still recommend, if you can find some kind of ROI a priori, to extract the individual effects from, then see if there's an interaction. Because just in general, as a rule of thumb, I should probably repeat this in case it wasn't picked up by the microphone, but if you've run an F test, you're trying to find out what's driving the effect, right? Is that right? Okay. Still, if the data goes into that model, it's still technically going to be, in my view, a bias analysis. So some people might disagree with me, but I think it would be a lot easier, and you wouldn't raise yourself to suspicion if you simply picked an ROI beforehand to extract the individual components from and then run an interaction test on that. That's what I would recommend. Yeah?
Does it introduce any type of bias by like making the assumption beforehand of what region you want to look at? And, like, how do you pick that region? Is it just a
Good question.
search to see like what regions are commonly associated?
Good question. This is actually kind of what I was going to talk about next. Can I read your mind? Have you already looked at it, right, before you pick the ROI? Does that make sense? So if you've picked it before you've analyzed anything, okay, so you've run the experiment, you haven't done the analysis, you don't know where the significant voxels are going to be. If you then pick an ROI and you say, this is the one I'm going to use for these theoretical reasons, because this is where other people found the effect, that's fine, because that ROI you've picked is not influenced by your data at all. In fact, I mean, we'd want to pick an ROI that would have some guess that we're going to find an effect there. We just don't want it to be artificially helped by the data, by using the data to define it. Yeah.
How do you go about like discovering the effects or like finding new regions that are associated?
Well, yeah, so there's obviously a place for exploratory analyses, but when we're talking about these so-called confirmatory or region of interest analyses, you don't want your criteria for doing the inferential statistics to be defined by only your significant, your strongest voxels, if that makes sense. Yeah? I'll get to one more example in a second. Yeah?
So I know that one way to pull those regions is using like existing masks that are based on meta-analyses.
Yeah.
Do you view that at all as problematic, given that the articles that may have gone into the meta-analytic mask could be biased themselves?
That is true, yeah. Right. So the question was, if you use a map based on a meta-analysis, are we still dealing with that file drawer problem where we're only selecting studies that have reported the most significant effects? I grant that could be an issue with, say, the effect size, but as for locating where the effect is, assuming that they've corrected for multiple comparisons in their studies, I don't think that should be a problem. And those meta-analyses maps are valid, in my opinion. Just as a rider to this example I'm giving, so I was on a study. It wasn't random. Sorry, I had to. I'm an egomaniac. They actually asked us to do another analysis where they said, well, can you use a meta-analysis? I'll show you this in a second. It's called NeuroSense. Very useful tool. You can do meta-analyses on the fly. If you haven't heard of this, it's an excellent website. Very useful. They said, well, can you still make this kind of distinction? Our main goal was, is there a ventral dorsal distinction between pain and, say, these more cognitive effects? And they said, well, do a meta-analysis for, say, pain and one for, say, I think it was prediction error conflict. And we still got the same parcel. The meta-analysis was still more ventral, it was below the cingulus sulcus, and the more cognitive effects were dorsal to it. So we replicated the exact same pattern. So in my experience, these meta-analysis masks do work. It's another way to verify your results, let's say. Because if in one study you're finding something that's so radically different from what everybody else has found across these meta-analyses, that indicates that something may be wrong. It's not a guarantee, but if it's a pretty robust, widely studied effect, it probably should be in the same area. But that's an excellent question by Kelly. Okay, I'm going to learn everybody's name by the end of this thing. Maybe. Anita, Mike, Paul. Okay. Oh, yeah. Don't worry. I already knew Anita and Mike, so it's not fair. Good people. Good people. Okay. So, and this gets back to what Kelly was saying. So choosing the ROI ahead of time. Okay. Emphasis on ahead of time. Let's say that I'm doing what I just told you to do, which is the correct Boy Scout thing to do, totally honest. You pick the ROI beforehand, and then you run the analysis. So here's where I say, okay, I've collected all the data, haven't looked at the results yet, but here's the ROI I'm going to use, highlighted in red. That's where I'm going to extract my data from. And then I look at the results, and yeah, there's some significant voxels in there. There's also a lot of non-significant voxels, and my ROI analysis is actually not significant. That's a heartbreaker. Nobody likes that. But there's a solution. I thought, oh, well, actually I meant to use this one. There's another ROI. It's independent. It's based on some other study, maybe a meta-analysis, and I do my ROI analysis on that one, and I do get a significant effect. Whoops. So, is that biased? Seriously? But it's not derived from those data. So how can you say that? It's okay, right? Right? Well, come on. But how can you read my mind? This is a big problem. And you can see why. Because how do you know? How do you know what the person was thinking ahead of time, right? This is one of the strongest arguments in my view for pre-registered reports, because you have to choose it beforehand and stick to it. Again, I haven't done pre-registered reports, so I don't know all the details, but I think they do allow you some wiggle room if you want to do some exploratory stuff, but you got to be very clear about that. if you want to do so. I could be wrong, but so I mean, this is the trickiest one because you can't read the person's mind. Yeah.
Can I ask a devil's advocate question?
Sure.
Say you picked the ROI that was more, less Dorsey.
Mm-hmm.
And okay, it's not my ROI, it isn't significant.
Mhm.
The publications that you publish are not significant. And that ROI is based on previous group points. What if the true effect is actually more dorsal? And now we quote unquote missed it
Mm-hmm.
because we had an a priori ROI that didn't work out. Do we
Yeah.
also have a responsibility to look for things that are outside our ROI, given the expense and the
Yeah.
burden of getting into it?
Good question. So the question was, what if the effect actually was in a different location from where you picked a priori? You don't want to do bias analysis, but you don't want to miss what the true effects are. I mean, that is why I would report both whole brain analyses and the other ones. The idea being that if enough people report whole brain analyses in the same area, that triangulates around where the true effect is. But kind of moving your searchlight around and saying, well, no, I think it was over here. Yeah.
Sure, of course, that one's
Yeah. We've all been there. It's okay. Have a. Yeah. I was going to make a stupid joke. It wouldn't even make sense. May as well tell it. I was going to be like, it's. No. Like a confessional group, like, oh yeah, my name's Andy, I do bias analyses, but just to, it's okay, and you can. Not that I've ever done it. Okay, see, you thought it was stupid, so I'll just keep that stuff to myself from now on. All right, so as we're wrapping up this bias analysis section, so some resources to do these independent ROI analyses. Okay, so one, as I mentioned, if you choose an ROI that is not derived from the data, right? So atlases are a good option. This is one example, the Harvard-Oxford Atlas. This comes with FSL. Parcelates the brain based on anatomical landmarks. So sulci, gyri, so on and so forth. Parcelates it so that certain regions are defined by anatomical boundaries. There are different ways to do parcelations, to do atlases. You can do it by Brodmann's areas, which was based on histology. You can do it by, say, multimodal parcelations like Glasser, Glasser, was the person who did that. Anyway, so atlases, just in general. On the book, if you just Google atlases, non-biased ROIs, you'll get a list of resources you can use for that as well. And neurosynth, again, something I was talking about earlier. When we get to functional connectivity, I'll be giving a fuller demonstration of neurosynth because it also has a way to generate functional connectivity maps. But for now, just be aware of the address, neurosynth.org. Very useful, does meta-analyses on the fly. So for example, if I type in a search term like working memory, here's the meta-analysis map that is returned. And then you can download these clusters and use them as your mask for ROI analysis. Yeah, I'm just thinking, as I'm saying things like mask, ROI analysis, I know there's some people here who may not have encountered that or may be slightly new to it. Just bear with me, and if you need any clarification about what I'm talking about, just feel free to let me know, either now or during one of the breaks, which is coming up shortly. 1 second here. I'm going to skip this animation. It's just showing in real time this leave one subject out cross-validation. References Esterman, 2010, if you want to learn more about that. In any case. Okay. So like I said, just to wrap this up in the interest of time, what to do about it. Choose an independent analysis. Make sure you do it beforehand, know the reasons behind doing it. And as we saw in that last example where we can kind of move the independent ROI around, that kind of independent analysis does not always guarantee non-biased results. I spent the most time on this because, again, it was this huge controversy just about 10 years ago, and it's still an issue in many cases. So I just want to make sure that everybody here has a good sense of when that issue might come up, because it's insidious. It can strike when you're not prepared for it. Okay. I'm going to go through a couple more things here, just a couple more controversies to be aware of, and some of them a little bit more recent, and then we'll take a break. So we had voodoo correlations, bias analyses. We had some back and forth, some papers, and we finally determined that bias analyses are bad. Here's how they happen. Here's what to do about it. And then we were done with problems, right? No. Then we had this thing come up in 2016, which, it seems like every 5 years or so there's another major crisis or something. But here's one of the most, say, well-known ones in recent memory. I was also alive when this happened, so very vivid memories of what occurred. But here's what happened. This was an article in the Proceedings of National Academy of Sciences, and the authors, Anders Eklund and some other authors, Tom Nichols was among them. This was their key phrase that set the world on fire. We found that the most common software packages for fMRI can result in false positive rates of up to 70%. These results question the validity of 40,000 fMRI studies. This was, I know this is being recorded, this is a very foolish thing to do, to say, because, this is virtually everything that's ever been published. And the media picks up on this, and of course this is, they're not like, let's take a second look at this. This may be a little overblown. They're like, oh my God, it's all crap, right? It's repent. It's over. It's over. And for a couple of months this was crazy. Even if in places like the Economist, for example, many different outlets, it was so-called cluster failure. It was a big problem. So. Okay, that was out of order. Sorry. Anyway, so why was this such a big problem? So they found an issue with how people were reporting these so-called cluster size effects. The reason this is such a big problem is the vast majority of studies do this so-called cluster extent thresholding. What does that mean? When I talked about the brain, this giant Rubik's Cube parcellated into voxels, voxels that are right next to each other aren't necessarily independent, right? If I tell you something about the signal in this voxel, you'll know something about the signal in its neighbor. You'll know something about the voxel a couple voxels down the road. And it kind of trails off the farther and farther away you get from it. Knowing that, we don't just correct for all of the different voxels that we have in the brain, which would be tens, hundreds of thousands. Instead, we look for clusters of voxels that are all individually past a certain significance level, right? Let me, again, I'm going to break out to show you a brief demonstration of how this works. So if you have the book open, if you type something like cluster correction, click on the very first one. I already had this written down, so I figured let's just use this. Okay, so if I just correct for every voxel individually, that's so-called Bonferroni correction, and here's the issue with it. Here's a typical functional image that I collect, right? You'll notice that the voxel at the center of B is mostly surrounded by brighter voxels in general. And A, the center of that, is mostly surrounded by darker voxels. So just knowing something about one of these gives us information about the other ones as well. And the same logic extends to the time course. Okay. So I know I'm zooming through this, but there's a video here. Don't click on this because then my voice is going to pop up in everybody's computers. It's going to be crazy. So I don't want to hear it. But let me just skip to where this demonstration is. Okay. So this is like a typical statistical map, right? That I've corrected for. And if I zoom in on this and I look at it at a slightly different angle, so let's say that the really brightly, like the more intense heat map are more significant voxels, and the bluer ones are less significant. If I look at this in a different area, so there's certain peaks, almost like mountain ranges. And if I look at this from a different angle, higher z-scores are going to correspond to higher peaks, right? When we threshold our image, when we give it, you threshold usually at like a p-value of 0.05, it corresponds to a certain z-value, for example. We're only going to see certain peaks above that, and those peaks can be consist of many different individual voxels. Whoops. Oh, I guess we can do that. So if we, say, have our threshold here at, say, 3.1, we only look at individual voxels that pass a z-value of 3.1, so only very, very strong ones. In other words, only these peaks are the ones that are going to remain from that thresholding. That initial cutoff is called a cluster-defining threshold. And depends what package you use. I cover this in all three of them on the book, but say in FSL, this is what you'd see in this Z threshold box right here. Okay. And I'll say if you use FSL, their defaults are fine. They don't seem to suffer from this problem. Whoops. Wait. Oh yeah. So anyway, so we have that. We have these peaks, these clusters. And then we run simulations to determine whether those individual peaks are significant. So here I've done my cluster defining threshold, and that has left these peaks remaining. So I've simply deleted everything that didn't pass that threshold and only have the strongest clusters that survive. So these clusters, are they significant? Are they what I would find due to chance? Yes or no? To find out, I need to run simulations to find that out. So let's say that my peak, this cluster right here is composed of 50 individual voxels that all pass that individual threshold. How often would we expect a cluster of that size due to chance? Well, if I know things about the data that went into it, things like the voxel resolution, the smoothness, I can generate a bunch of just noise data sets with those same parameters. And let's say I get something like this. And it also has, just by chance, a group of individual voxels. That's about 39 voxels. Another cluster, another simulation. I keep running these simulations, and I write down how big is the largest cluster from those simulations. I do this thousands of times. And I build up a distribution for what the cluster sizes should look like. Right? So I do this a lot. Again, these are just noise data sets. I'm running a bunch of simulations. And I compare this distribution to my cluster that I found in my data set. If it's, say, less than 5% of what I found in that distribution, then I can go ahead and say that, yeah, my cluster probably wasn't due to chance. It is a significant cluster. Makes sense? This all goes on under the hood. I kind of made this animation. These aren't like actual, no, this isn't what you'd actually see or whatever is happening under the hood with SPM, AFNI, FSL, and so on. But this is the basic idea of what's going on. Okay. So that's all fine, assuming that you have a correct estimate of what the smoothness of the data actually was going into these simulations. And what he found, this back up. Skip ahead here. So let's say, I ran all my simulations, and then I get my original clusters. And then, if I have a cluster list like this, I say, well, I ran the simulations. I would find clusters of 668, and do these clusters pass that threshold, yes or no? If they do, they're significant, and I can report them. Now, the problem with this was, okay, well, yeah, we can use some of these default thresholds. But there are a few problems, and the one that they focused on in the Eklund paper was the cluster simulations violate these parametric assumptions that we make. So we have assumptions about how dependent voxels are with their neighbors. We can model it as a function, actually, which I can show you. So we're going to focus on problem number 3, so these were assumptions at the time, and the major packages have corrected this for the most part. But they assume a few things. 1, spatial smoothness is constant over the entire brain. 2, spatial autocorrelation is normally distributed. Let me show you an example of what that looks like exactly. So 1, smoothness does not actually vary over the brain. There are certain parts of the brain, say in the midline regions, where the smoothness is a little bit higher, for example, and other regions where it is, in fact, lower. So that's one violation of their assumptions they make in those simulations. The second one, this was the real killer, is I can create a function about the correlation between a voxel and its neighbors. So down here, this is a voxel chosen at random. If I move 3 millimeters away from that voxel, they're about 0.8 correlated, 8% correlated, right? They share a lot of information. But as you'll see, what the original simulations tended to assume, and this is in the solid line right here, in Afni's original in their original correlation function, it had much larger tails. So it was assuming that there was more, say, correlation between one voxel and a voxel very far away than there actually was. So when they did this with simulations, they found out that the distribution actually looks different. And if you use that original distribution, the one in the solid line, you're going to get much more liberal cluster thresholds. In other words, you're going to have a lower threshold for determining whether a cluster is significant. And they included this figure, which showed that if you just use, say, the defaults in SPM or FSL, FSL has a thing called Flame. Afni has a few things like 3D t-test, 3D MIMA. If this solid line right here is your nominal point, your 5% false positive rate, their false positives were exceeding that almost across the board, which was a problem for the most part. What I have highlighted in permutation tests doesn't make any of these parametric assumptions. It simply takes the data and it uses that data to build up a distribution and then basically say, okay, given, say, I don't know, the contrast maps that I feed into it, if I build up a distribution of, say, random contrast by, say, switching the sign, for example, and then I look at my original contrast, is it beyond, say, the 5% threshold of what I've built up in this distribution? Kind of hard to visualize. I don't have an animation for it in this slide, but that's the basic idea. Their point was if you use permutation tests, you don't have this problem with cluster correction, these cluster correction thresholds. But I also want to point out, it's kind of hidden at the very top, but this was the graph that a lot of people were paying attention to. That uses a cluster defining threshold of p equals 0.01. This one is p equals 0.001. As you can see, it's not perfect, but the statistical packages do quite a bit better in that case. The upshot of all of this is either use permutation tests. You really can't go wrong with it. No one's going to ding you for it. Or if you do decide to use these cluster defining thresholds with the parametric assumptions, use a cluster defining threshold of 0.001 before you do your cluster inference. Those are really the main things. And unfortunately, I think it's been a little too simplified in that a reviewer might say, well, you're not using .001, therefore this isn't a valid test. That's not necessarily true. You can use a lower threshold. By that I mean a higher, closer to defining threshold, and it can still be a valid inference, but if you use the correct, like the updated cluster simulations that are now the defaults with the packages, you're going to get clusters that are too large to really make sense of. If a cluster spans multiple regions, it's really hard to make sense of where the activity is really located. That's the upshot of all of this. Okay. So basically what I just said, voxel-wise thresholds, not that widely used. That's the Bonferroni type analysis I was talking about, and we identified some problems with it because they aren't actually all independent tests. I will say that there is this whole debate between a balance between type 1, type 2 errors, false positives and false negatives. Obviously, you're going to be much more biased towards producing a lot of false negatives if you use a voxel-wise threshold. But there's virtually no scenario where you're going to get false positives. So it is good for that. Depends on what you're really trying to guard yourself against. Okay. We don't have time to go through, say, exercises to do all of these today, but I will say that, I keep saying this, on the book there are examples about how to do this in all 3 packages. I'm curious, how many people primarily use SPM to analyze their data? Okay. FSL? AFNI? Ooh. Anybody else? I think that's the other person. Yeah. I grew up on AFNI, so I have a special connection with that software package. I like their sense of humor. That's their saving grace. Let's see here. We're almost at 11. I just have a few more slides. I'm going to be a little selective. Originally, I was going to talk a little bit about open science, reproducibility, which we've touched on a little bit. I'm going to, just in the interest of time, I'm going to kind of skip over that because it's not necessarily a pitfall, but it's something to be aware of in case you want to, I don't know, guard yourself from, what's the word? Kind of clerical errors, like kind of. What I was going to talk about is something called bids, but we'll get to that eventually when we look at the data set that we're analyzing. So if it's okay with everybody, I'm not going to cover the reproducibility part of it. We'll see how far I get. I have 10 minutes. But a few more things to be aware of. These are statistical fallacies. So we talked about multiple comparisons correction. We talked about so-called voodoo correlations, bias analyses, and also some things to be on guard against with cluster correction. Now, assuming even you've done everything correctly, okay, you've guarded against false positives, you've done an independent analysis, all the data you're looking at in your stats package is in fact correct, let's say, right? There's still the inference that needs to be made about it. So just to make sure we're on the same page, these region of interest analyses, these are averages across the voxels within a mask. What is a mask? When we collect an fMRI data set, we have all these voxels. Usually we're not interested in every individual voxel, right? If I'm only interested in, say, the dorsal anterior cingulate cortex, for example, I can create a mask in which I highlight or indicate only those voxels belonging to the region that I am interested in. I could have multiple ROIs, regions of interest, but by definition, it's a circumscribed set of voxels within the larger data set. That's what a mask is. People use masks and regions of interest interchangeably, or at least I do. Not the same thing as small volume correction in which you have a mask, but it's almost like you're doing an additional whole brain analysis within that mask. The ROI analysis is you average across all the data within the mask, if that makes sense. That's what I'm going to focus on right here. So let's say, for example, instead of reaction time, think of these as beta weights. And they wouldn't be this large, but that's kind of the idea. So I extract some data from an ROI. Let's say I have two groups, male, female, and it's an incongruent and a control condition, like some cognitive control test. This is really, I just kind of made this up on the fly. I'm terrible with coming up with these examples. I'm really trying to work on it, but if it's boring as hell, I'm sorry. But there's an incongruent thing, and are there differences between males and females? Oh my God, no one's ever investigated this before. Although literature has looked at, I don't know, whatever. See, I can't even come up with that. We're almost due for a break. Don't worry. Okay, but let's say we have something like this, right? So we're trying to determine whether there's, say, some kind of interaction between these conditions and groups that we've extracted from. Okay, so this is like a typical scenario what you do with the data after you've done the ROI analysis. Now, there is let's see here. Yeah, right here. What a lot of people were doing is, they would do things like that. They would extract data for, say, a couple conditions or a couple ROIs. Let's say do it like a condition by ROI interaction or condition by group interaction. And they were claiming something called a double dissociation, which you may come across. It's a very powerful statistical test that can give you insight into the specificity of function for a couple of regions. Because you're saying it is active for one condition but not the other condition, and vice versa, which is great. But what some people were doing, and this was a Nature paper, Nature Neuroscience, I believe, basically exposing this statistical fallacy. If I have, let's see, what would be a good example here? Let's say that I have two conditions, and they did this across a bunch of different studies, different modalities, different, not just imaging, but other experiments as well. If I have, say, a condition right here, which is, significantly positive, and another one that's also, say, significantly positive over here. Oh, sorry, no, don't go there. Sorry, this is the one I want to focus on. So let's say that I have a significantly positive effect in this condition and a non-significant effect over here. That does not necessarily imply that the difference between them is statistically significant. You have to run an individual test to do that. Let's say a paired or between groups t-test for that. Likewise, if you're trying to make some kind of inference about a double dissociation, you need to test a few things. Let's say I'm focusing on this section right here, B. If I want to make a claim about double dissociation, let's say that these were brain regions and these were, say, different conditions, for example, and I want to make the case that there's a significant effect in, this ROI here, but not here, and, say, vice versa for the other one. You need to test a few things. First of all, within an ROI, you need to compare them directly, right, in each one. So in this case, I want to make sure that this is significantly greater than that. And if it were true double dissociation, this other one would be significantly greater than the one in black. And also a test for the interaction between the two. And not many people do this. If they just find, say, they may look at an ROI and say it's significant for this condition, but not this one, therefore double association. Not necessarily true. You have to start to compare them to determine if they're significantly different. Also very useful to actually unpack the contrast and interactions if you're trying to do this type of test. So again, pretty vanilla experiment. Let's say I do something like left minus right button presses. Okay, I'm trying to find some double dissociation between the left motor cortex and the right motor cortex. If I simply extract the data for left minus right, let's say I'm focusing on the right motor cortex, it could be that what's creating this is, left is actually greater than right. It could be that right is more negative than left, or it could be a combination of the two, right? So I hope that makes sense. I mean, these all mathematically come out to the same thing. If there's, say, left is slightly positive, but I'm subtracting a negative, the overall result of left minus right is going to be highly positive. Same thing if left is much more positive than right, and so on. But the point is, if you want to make any kind of claim about which of these regions is selective for a certain effect, you need to look at the individual contrasts and compare them directly. And again, for double associations, let me just get to the part that I want here. This is what a really clean, say, double dissociation would look like. Let's assume that these error bars are like, I don't know, one standard error. So for argument's sake, let's say that right was actually significant. Okay, we're looking at the left motor cortex right here. Right is significantly positive, and let's say, just for argument's sake, left is, there's no significant difference from baseline. And over here we have the exact same pattern, but it's flipped in the right motor cortex, right? So left is significant, right's not. And if I directly compare these two, in each, there's a significant difference between them. And the interaction for ROI by condition is also significant. So if I check off all those check boxes, interaction, t-test between the two, one is positive, one's not significant, then I would say that there is a double association. Pretty common scenario that you'll come across. Okay, any questions so far? Okay, let's take been here a while, let's take a 10-minute break. Sound good? Meet back here at 11:10. Any questions about what I talked about so far? You want some more information about those resources? You can come talk to me if you want to.